This video is part 2 of my previous video. Last time we discussed some general methods for control of particulate matter emissions, which included gravity and momentum collectors, centrifugal collectors, fabric filters, electrostatic precipitators, and wet particulate scrubbers. We have already discussed first two types. So today let's start with the fabric filters. Fabric filtration is one of the most common techniques to collect particulate matter from industrial waste gases. The use of fabric filters is based on the principle of filtration, which is a reliable, efficient, and economic method to remove particulate matter from the gases. The air pollution control equipment using fabric filters are known as baghouses. Now, what exactly are fabric filters, also called baghouses? These are devices that remove particulate from a gas stream by passing the dirty air through a layer of cloth. Particulate matter deposits on the cloth surface, leaving only the clean air to pass through. As the most prevalent control device used in modern industrial processes, fabric filters are considered to have a great importance. Most baghouses use long cylindrical bags or tubes made of woven or felted fabric as a filter medium. For applications where there is relatively low dust loading and gas temperatures are almost 121 degrees Celsius or less, pleated, non-woven cartridges are sometimes used as filtering media instead of bags. Dust-laden gas or air enters the baghouse through hoppers and is directed into the baghouse compartments. The gas is drawn through the bags either on the inside or the outside depending on cleaning method, and a layer of dust accumulates on the filter media surface until air can no longer move through it. When a sufficient pressure drop occurs, the cleaning process begins. Cleaning can take place while the baghouse is online, means it's filtering, or is offline, means it's in isolation. When the compartment is clean, normal filtering resumes. Baghouses are very efficient particulate collectors because of the dust cake formed on the surface of the bags. The fabric provides a surface on which the dust collects through the following four mechanisms. Inertial collection. Dust particles strike the fibers placed perpendicular to the gas flow direction instead of changing direction with the gas stream. Number 2. Interception. Particles that do not cross the fluid streamlines come in contact with fibers because of the fiber size. Then comes Brownian movement. Submicrometer particles are diffused, increasing the probability of contact between the particles and collecting surfaces. Electrostatic forces, the presence of an electrostatic charge on the particles and the filter can increase dust capture. A combination of these mechanisms results in formation of the dust cake on the filter, which eventually increases the resistance to gas flow. The filter must be cleaned periodically. There are three types of fabric filter cleaning methods. Number 1, reverse air. Number 2, shaker. And number 3, pulse jet. Each method has been developed to respond to the specific applications. In mechanical shaker baghouses, tubular filter bags are fastened onto a plate at the bottom of the baghouse and suspended from horizontal beams at the top. Dirty gas enters the bottom of the baghouse and passes through the filter, and the dust collects on the inside surface of the bags. Shaker baghouses range in size from small hand shaker devices to large compartmentalized units. They can operate intermittently or continuously. Intermittent units can be used when processes operate on a batch basis. When a batch is completed, the baghouse can be cleaned. Continuous processes use compartmentalized baghouses. When one compartment is being cleaned, the airflow can be diverted to the other compartments. The air-to-cloth ratio for shaker baghouses is relatively low, hence the space requirements are quite high. However, because of the simplicity of design, they are popular in the mineral processing industry. In reverse air baghouses, the bags are fastened onto a plate at the bottom of the baghouse, and suspended from an adjustable hanger frame at the top. Dirty gas flow normally enters the baghouse and passes through the bag from the inside, and the dust collects on the inside of the bags. Reverse air baghouses are compartmentalized to allow continuous operation. Space requirements for a reverse air baghouse are comparable to those of a shaker baghouse. However, maintenance needs are somewhat greater. In reverse pulse jet baghouses, individual bags are supported by a metal cage, also called filter cage, which is fastened onto a plate at the top of the baghouse. Dirty gas enters from the bottom of the baghouse and flows from outside to inside the bags. The metal cage prevents collapse of the bag. Reverse pulse jet dust collectors can be operated continuously, but they are usually not compartmentalized. Woven and felted materials are used to make bag filters. Woven filters are used with low energy cleaning methods such as shaking and reverse air. Felted fabrics are also used with low energy cleaning systems such as pulse jet cleaning. While selecting the filter medium for baghouse, the characteristics and properties of the carrier gas and dust particles should be considered. The properties which must be noted include carrier gas temperature, carrier gas composition, gas flow rate, size and shape of dust particles, and its concentration. The abrasion resistance, chemical resistance, tensile strength, permeability, and the cost of the fabric must be considered. The fibers used for fabric filters can vary depending upon the industrial application. Some filters are made from natural fibers such as cotton or wool. These fibers are relatively inexpensive but have temperature limitations and only average abrasion resistance. Cotton is readily available, making it very popular for low temperature simple applications. Wool withstands moisture very well and can be made into thick felts easily. Synthetic fibers such as nylon and polyester have slightly higher temperature limitations and chemical resistance. Synthetic fibers are more expensive than natural fibers. The efficiency of a bag filter may decrease on account of the following factors. Excessive filter ratios. Filter ratio is defined as the ratio of the carrier gas volume to gross filter area per minute flow of the gas. Excessive filter ratios lower particulate removal efficiency and result in increased bag wear. Therefore, low filter ratios are recommended for high concentration of particulate. Improper selection of filter media. While selecting filter media, properties such as temperature resistance, resistance to chemical attack, and abrasion resistance should be taken into consideration. Various problems during the operation of a bag house include cleaning. At intervals, the bags get clogged up with a covering of dust particles that the gas can no longer pass through them. At that point, the bags have to be cleaned by wrapping, shaking, or by reverse airflow by a pulse jet. Rupture of the cloth. The greatest problem inherent in cloth filters is the rupture of cloth, which results from shaking. It is often difficult to locate ruptures, and when they are found, the replacement time is often considerable. Temperature. Fabric filters will not perform properly if a gross temperature overload occurs. If the gas temperature is expected to fluctuate, a fiber material that will sustain the upper temperature fluctuation must be selected. Also, whenever the effluent contains a reactive gas like sulfur dioxide, which can form an acid, whenever the temperature in the bag house falls below the dew point, it can create problems. Sometimes, it may even be necessary to provide an auxiliary heater to make sure that the temperature in the bag house does not fall below acid gas dew point. Bleeding. This is the penetration of the fabric by fine particle, which is common in fabric filtration. It can occur if the weave is too open or the filter ratio is very high. The solution is to use a double layer material or a thick woven fabric. Humidity. This is a common and important problem, especially if the dust is hygroscopic. It would therefore be advisable to maintain moisture-free condition within the bag house as a precautionary measure. Chemical attack. This is another problem associated with fabric filters. The possibility of chemical attack due to corrosive chemicals present in the effluent. A proper choice of fabric filter will avoid this problem. The advantages of fabric filter are high collection efficiencies for all particle sizes, especially for particles smaller than 10 micron in diameter, simple construction and operation, nominal power consumption, dry disposal of collected material. The disadvantages of a fabric filter are operating limits are imposed by high carrier gas temperatures, high humidity, and other parameters. High maintenance and fabric replacement costs. Baghouses are difficult to maintain because of the difficulty in finding and replacing even a single leaking bag. Also, as general rule, about 1/4 of the bags will need replacement every year. Large size equipment. Problems in handling dust, which may abrade, corrode, or blind the cloth. Fabric filters find extensive application in the following industries and operations: metallurgical industry, foundries, cement industry, chalk and lime plants, brickworks, ceramic industry, and flour mills. A bag filter is comparatively expensive to install. Its power consumption is moderate. In most cases, the maintenance cost is high because the bags have to be repaired or replaced regularly. The nature of the gas and the dust decide the frequency of such maintenance work. Let's talk about the fourth control technology for particulate matter emission, and it is electrostatic precipitators, which are also called as ESP. These are particulate collection devices that use electrostatic force to remove the particles less than 5 micron in diameter. It is difficult to use gravity settlers and cyclones effectively for the sets range of particles. Particles as small as 1/10 of a micrometer can be removed with almost 100% efficiency using electrostatic precipitators. The working principle of the electrostatic precipitator is quite simple. It has two sets of electrodes, one is positive and the other is negative. The negative electrodes are in the form of rod or wire mesh. Positive electrodes are in the form of plates. The positive plates and negative electrodes are placed vertically in the electrostatic precipitator alternatively one after another. The negative electrodes are connected to a negative terminal of high voltage DC source, and positive plates are connected to the positive terminal of the DC source. The positive terminal of the DC source may also be grounded to get stronger negativity in the negative electrodes. The distance between each negative electrode and positive plate and the DC voltage applied across them are so adjusted that the voltage gradient between each negative electrode and adjacent positive plate becomes quite high so that they can ionize the medium between them. The medium between the electrodes is air, and due to the high negativity of negative electrodes, there may be a corona discharge surrounding the negative electrode rods or wire mesh. Corona discharge is actually an electrical discharge brought by the ionization of a fluid, for example air. The air molecules in the field between the electrodes become ionized, and hence there will be plenty of free electrons and ions in the space now. The entire system is enclosed by a metallic container on which one side is provided with an inlet of the flue gases and the opposite side is provided with the outlet of the filtered gases. As soon as the flue gases enter into the electrostatic precipitator, dust particles in the gases collide with the free electrons available in the medium between the electrodes, and the free electrons will be attached to the dust particles. As a result, the dust particles become negatively charged. Then these negatively charged particles will be attracted due to electrostatic force to the positive plates. Consequently, the charged dust particles move towards the positive plates and get deposited on them. Here, the extra electron from the dust particles will be removed on positive plates, and the particles then fall due to gravitational force. We call the positive plates as collecting plates. The flue gases, after traveling through the electrostatic precipitator, become almost free from ash particles and ultimately gets discharged to the atmosphere through the chimney. An electrostatic precipitator does not contribute directly to the production of electricity in the thermal power plant, but it helps to keep the atmosphere clean, which is quite important for living beings. Hoppers are fitted below the electrostatic precipitator chamber for collecting dust particles. Water spray may be used on the top to accelerate the removal of the dust from the collecting plates. There are three types of electrostatic precipitators which are commonly known. Number 1, single stage or two stage. Number 2, pipe type or plate type. Number 3, dry and wet precipitators. Generally, the collection efficiency of the electrostatic precipitator is very high, approaching 100%. Many installations operate at 98 to 99% efficiency. Some materials ionize more readily than others and are thus more adapted to removal by electrostatic precipitation. Acid mists and catalyst recovery units have efficiencies in excess of 99%. However, for materials like carbon black, which have very low efficiencies due to very low collection capacity, by proper combination of an ESP with a cyclone, very high efficiencies can be achieved. The gas entering the ESP may be pre-treated, that is, removing a portion of particulate matter by using certain mechanical collectors or by adding certain chemicals to the gas to change the chemical properties of the gas to increase their capacity to collect on the discharge electrodes and thus increase the efficiency. The factors affecting the efficiency of electrostatic precipitators are particle resistivity and particle re-entrainment. The advantages of using the ESP are high collection efficiency. Particles as small as 0.1 micron can be removed. Low maintenance and operation cost. Low pressure drop. Satisfactory handling of a large volume of high temperature gas. Treatment time is almost negligible. Cleaning is easy by removing the units of precipitator from operation. There is no limit to solid, liquid or corrosive chemical usage. Some disadvantages of using the ESP are high initial cost. Space requirement is more because of the large size of the equipment. Possible explosion hazards during collection of combustible gases or particulate matter. Precautions are necessary to maintain safety during operation. Proper gas flow distribution, particulate conductivity, and corona spark over rate must be carefully maintained. Lastly, the negatively charged electrodes during gas ionization produce ozone. Important applications of ESPs in different industries throughout the world are cement factories, pulp and paper mills, steel plants, non-ferrous metal industry, chemical industry, petroleum industry, carbon black industry, and electric power industry. Now let's talk about the fifth technology and the last one for the control of particulate matter emissions, that is scrubbers. Scrubbers are devices that remove particulate matter by contacting the dirty gas stream with liquid drops. Generally, water is used as the scrubbing liquid. In a wet collector, the dust is agglomerated with water and then separated from the gas together with the water. The mechanism of particulate collection and removal by a scrubber can be described as a four-step process. Number 1. Transport. The particle must be transported to the vicinity of the water droplets, which are usually 10 to 1000 times larger. Number 2. Collision. The particle must collide with the droplet. Number 3. Adhesion. This is promoted by the surface tension property. Number 4. Precipitation. This involves the removal of the droplets containing the dust particles from the gas phase. The physical principles involved in the operation of the scrubbers are impingement, interception, diffusion, and condensation. When gas containing dust is swept through an area containing liquid droplets, dust particles will impinge upon the droplets, and if they adhere, they will be collected by them. If the liquid droplet is approximately 100 to 300 times bigger than the dust particle, the collection efficiency of the particles is more because the numbers of elastic collisions increase. Number 2 is interception. Particles that move with the gas stream may not impinge on the droplets but can be captured because they brush against the droplet and adhere there. This is known as interception. Number 3. Diffusion. Diffusion of the particulate matter on the liquid mediums helps in the removal of the particulate matter. Number 4. Condensation. Condensation of the liquid medium on the particulate matter increases the size and weight of the particles. This helps in easy removal of the particles. The various types of scrubbers are spray towers, Venturi scrubbers, cyclone scrubbers, packed scrubbers, and mechanical scrubbers. The simpler types of scrubbers with low energy inputs are effective in collecting particles above 5 to 10 micron in diameter, while the more efficient, high energy input scrubbers will perform efficiently for collection of particles as small as 1 to 2 micron in diameter. The advantages of the scrubbers are low initial cost, moderately high collection efficiency for small particles, applicable for high temperature installations. They can simultaneously remove particles and gases. There is no particle re-entrainment. Some disadvantages of scrubbers are high power consumption for higher efficiency, moderate to high maintenance cost owing to corrosion and abrasion, and lastly, wet disposal of the collected material. The scrubbers are used in a variety of applications. Some of them are as follows. They are particularly useful in the case of a hot gas that must be cooled for some reason. If the particulate matter is combustible or if any flammable gas is present, even in trace amounts, in the bulk gas phase, a scrubber is preferred to an electrostatic precipitator. Scrubbers can be used when there are wastewater treatment systems available on the site with adequate reverse capacity to handle the liquid effluent. Scrubbers are also used when gas reaction and absorption are required simultaneously with particulate control.